In this video, we're going to look at some of the user controls. All right, let's start with the black box and the blue box. These two boxes can be dragged by the user. That's one of the user controls. And what it does is this is going to change the intercepts, and basically we're going to be changing the value of beta 0 and beta 2. Beta 0 is the intercept of the black line, and beta 2 is the difference between the two intercepts, the intercept of the black line and the blue line. So this is changing parameters, and that's what we're doing. And when the parameters change, the samples get translated with it. So you see this blue sample is translated upwards when I move the blue line upwards. Okay, and the user can observe what happens when we increase the difference between the black group and the blue group. The significance of the model increases. In fact, this F statistic increases. So let's see, let's bring this a little further apart, and we see we increase the F statistic, increasing the significance. So if we bring it close together, very close together, eventually the significance is going to turn to no. Okay, the F statistic decreases and the model is no longer significant, and this is at the alpha equal 0.05 level. Here are two more user controls, the black diamond and the blue diamond, and that will change the slope of the lines. Okay, so that changes the value of beta 1. Notice that changing the slope does not affect the F statistic. It does not affect the significance of the model. And this makes sense because the slope has to do with the variable x1, and we want to eliminate the effect of x1. In fact, if the slope is 0, then ANCOVA changes to analysis of variance. Okay, at this point I want to talk about the standard deviation sigma. Okay, here's our model. Our model sometimes is written in the following form. Random value y is equal to this part of the model, which is the same as the expected value of y, plus epsilon, where epsilon is a random variable whose mean is 0 and whose standard deviation is sigma. So we assume that that y given a particular value for x1 and x2 has the standard deviation of sigma. Okay, so now let's go back to our applet and see the role that sigma plays. So in our applet, sigma has to do with how close the sample points hug the sample lines. All right, so let's say here we can adjust the value of sigma. Let's say if we make sigma smaller, if we choose sigma equal to 10, you see how the sample points move close to the sample lines. And if we increase to 50, we see they spread apart. We should also notice that this yellow bar here, which represents what we call an error sum of squares, increases with sigma. We'll be talking about the bar graph soon. But notice when sigma is 10, this bar is very small. And when sigma is 50, this bar increases in size. Also notice that when sigma is smaller, the model becomes more significant. Okay, here we have, when sigma is 50, we have this F statistic of 16.4. Let's change sigma to 10, and we see how the F statistic increased to 365, and you can see that the influence of x2, the factor variable, is greater because there's a greater distinction between the blue points and the black points when sigma is smaller. Okay, pressing this new sample button will draw a new sample from the same population. Okay, so notice that I set sigma to 50 and beta 2 is equal to 60. Okay, beta 2 is definitely non-zero. And here the significance of this model, we do conclude that this model is significant based on this sample. If we choose a new sample, notice that the significance is now no. Okay, and if you look at the sample lines, they don't seem to closely approximate the parameter lines, so that's why this particular sample led to the conclusion that this model is not significant, or that the blue and the black groups are not significantly different. And if you look at the blue and the black points, they do seem to be intermingled. Okay, we don't see a very stark distinction between them. If we can keep repeatedly choosing a new sample and observe if the significance changes. So just look at this significance here as we take new samples, and sometimes it's yes and sometimes it's no. And we could count the percentage of yeses and nos, and from this we learn something about the type 2 error. So if we do this experiment, draw samples repeatedly, we'll notice that this particular model is significant approximately 62% of the time and insignificant approximately 38%. Now, the 38% represents the probability of a type 2 error, because this model is significant. In other words, we do see that beta 2 is 60. Beta 2 is non-zero. And yet 38% of the time we can't detect the fact that beta 2 is non-zero. So 38% represents the probability of a type 2 error. That is, H0 is not rejected when H0 is false. Here the user can change the sample size, and notice that increasing the sample size tends to increase model significance, and we can also observe that it decreases the type 2 error.